Good morning. Today we will see another tutorial on reciprocating pump. In this tutorial session, we will attempt three numerical problems on reciprocating pump. So the first problem: a single-acting, single-cylinder reciprocating pump has stroke length of 400 mm and piston diameter of 400 mm. The pump runs at 20 rpm. The suction and delivery head are 4 meter and 20 meter. The length of suction and delivery pipe are 6 meter and 25 meter, and the diameter of the suction and delivery pipe is 200 mm. Estimate the power required to drive the pump if the coefficient of friction in pipe is 0.02. So you are asked to determine the theoretical power needed for operating the pump for the given set of inlet exit data of the pump. So let us first of all write down the given data, identify the given data. So it is given that the reciprocating pump is a single acting single cylinder. We can mention below given or given of data given are pump has a stroke length of 400 mm, and piston diameter equal to, that is also 400 mm. Then speed of rotation of the pump n 20 rpm. Then suction and delivery head, that is HS, suction head HS is 4 meter, and delivery head HD 20 meter. The length of suction and delivery pipe. So we have given the length of the suction and delivery pipe. LS, length of the suction pipe is 6 meter, and that of delivery pipe is 25 meter. Then diameters of suction pipe and delivery pipe both are 200 mm. Then friction coefficient is 0.02. These are the data specified for the pump, and it is a single acting. Also we can write here, this is a single acting and single cylinder, only one cylinder. So these are the known that are related to the pump. Now let us start solving for the power requirement of the pump. The right solution. Since the speed is specified, we can calculate the angular speed omega. So the angular speed omega we can calculate using the relation 2 pi n by 60. So that is equal to 2 pi into 20 by 60. So after calculating, we will get this as equal to 2.093 farad per second. Farad per second. So 2 pi n by farad per second. Then the crank radius R is, it has equal to half of the stroke length. So it is 400 by 2, which will be equal to 200 mm. So we can write this as equal to 200 mm means it is R equal to 0.2 meter. Now to find the power requirement of the pump, here nothing mentioned about the air vessels fitted in the suction and delivery side. So we can write the power requirement, the equation for the power, the theoretical power required for the pump. So theoretical power, if it is P equal to gamma A n by 60 L into Hs plus Hd plus 2/3 of HFS plus 2/3 of HFD. So this is the total head, the total head. So this is the total head that has to overcome by the pump. In this HS, HD are given, only thing is that we have to calculate the frictional head in the suction and delivery pipe. So that we can calculate by using the Darcy's equation. So the frictional head loss in suction pipe HFS, this is equal to 4F LS 3A square divided by 2G S. In this equation, Vs is the velocity of the fluid when the piston is at the center of the cylinder, that is crank angle theta equal to 90 degree. So Vs, fluid velocity in the suction pipe when theta equal to 90 degree. This is Vs. So this is, this as equal to A by or AP by AS omega R. Actually, velocity, instantaneous velocity V, this as A by AP by A omega R sin theta. So when theta equal to 90 degree, V equal to AP by A omega R. So this equation we have derived in our lecture class. So now let us substitute and find the frictional head loss in the suction pipe. So HFS equal to 4 F LS. For V, we may put this equation AP by AS omega R square divided by 2G. Now, since the dimension of the suction pipe are given, we can easily find out the frictional head loss in the suction pipe. So HFS equal to 4 into F value 0.02 into suction pipe length is 6 meter. This into area of the cylinder or piston area, which is 5 by 4, diameter is into 0.4 square divided by AS suction pipe area 5 by 4 into 0.2 square is into omega we got as 2.093 into R we got as 0.2 meter. So it is 0.2 this square or divided by 2 into 9.81 into diameter between 0.2. So if we calculate, we will get this as equal to 0.342 meter. So this is the frictional head loss in suction pipe. Similarly, we can calculate the head loss due to friction in the delivery pipe. So HFD, we can write here friction head loss in the delivery pipe. Delivery pipe HFD equal to 4F LD. That time we have to put BD square by 2G PD. Again, velocity we can calculate by putting the previous equation, but we have written for the velocity in the suction pipe. Only thing we have to substitute the diameter of the delivery pipe. So in this case, both the diameters are equal, so the area and the velocity will be 4 into F LD. This is AP by, instead of AS, it is AD into omega R square by 2G AD. So now let us put the dimensions of the delivery pipe here. So that is equal to 4 into 0.02 into length of the delivery pipe is 25 meter. So this is 25 into area of the piston is same, maybe 4 into 0.4 square by that of delivery pipe Also the same diameter is same, so it is point maybe for the point 2 square into omega 2.093 into tan point 2 square divided by 2 into 9.812 into diameter of the is also point 2. Diameter of the delivery pipe is also point 2. So you calculate, you will get this as equal to 1.43 meter. So this is your friction head loss in delivery pipe. 1.43 meter in the delivery pipe. Now we can substitute the frictional head loss values that we obtained and the given suction and delivery lift delivery heads, the equation for the power. So the power required P equal to gamma A n by 60 PL into HS plus HD plus 2/3 of HFS plus 2/3 of HFD. So this is equal to gamma is specific weight of water, so it is 9810 into area of the, we'll put this as AP, actually no, this AP piston for the cylinder area, so 5 by 4 into 0.4 square RPM 20 by P into length, stroke length is again this 4, so we'll put this 0.4 into HS suction head value, it is 4 meter plus delivery head is 20 plus 2/3 of, let us put into 0.342 plus 2/3 of 1.43. So this is the theoretical power that is required to drive the given centrifugal pump, and substitute and calculate the values. Finally, you will get the power required as equal to 4.2 kilowatt. Will be the power requirement of the given single cylinder, single acting reciprocating pump. Okay, so that completes our first problem. Now let us move on to the next problem. So the second problem, find the maximum speed of a single acting reciprocating pump to avoid separation, which occurs at 3 meters of water absolute. The pump has a cylinder of diameter 10 centimeter and a stroke length of 20 centimeter. The pump draws water from a sump and delivers to a tank. The water level in the sump is 3.5 meters below the pump axis, and the delivery tank, the water level is 13 meters above the pump axis. The diameter and length of the suction pipe are 4 centimeter and 5 centimeter respectively, while the delivery pipe has length of 20 meter and diameter of 3 centimeter. Assume atmospheric pressure at 10.3 meter of water. So in this problem, we are asked to determine the maximum speed with which the pump can be operated without fearing separation. And the separation occurs at 3 meters of water absolute. So let us first of all write down the given data here. So given given the separation pressure, that is H separation. Let us say it is 3 meter and that is absolute value, absolute 3 meters of water, absolute. Then the pump has a cylinder and diameter of the cylinder is 10 centimeter and the stroke length 20 centimeter. Then water level in the sump is 3.5 meter below the pump axis. So the water surface, the distance between the water surface and the pump axis is 3.5 meter, means it is suction head. So we have given HS as equal to 3.5 meter. Then the delivery tank water level is 13 meter above the pump axis. That means the distance between the water level in the delivery tank and the pump axis, that is delivery head, for the height of the water surface above the pump axis, it is 13 meter. The suction pipe diameter is 4 centimeter. Suction pipe diameter 4 centimeter and length of the suction pipe is 5 centimeter. Then the delivery pipe diameter is 3 centimeter. Delivery pipe diameter 3 centimeter and its length is 20 meters. So these are the data given to us. So let us make a small correction. You take this length as 5 meter. So this question it is 5 not 5 centimeter, it is 5 meter. It's 5 meter. The length of the suction pipe is 5 meter. So these are the data given, and we're asked to find, question is to find n maximum. So this is what you want to calculate. So there is now to find the maximum speed. Let us now consider the modified indicator diagram of a single acting single cylinder reciprocating pump. So this diagram represents the indicator diagram by taking into account the effect of friction and acceleration. So with respect to this indicator diagram, we can understand that during the suction stroke, the minimum pressure or the lowest pressure occurs corresponding to tank angle theta equal to 0, or the location is the point where the minimum pressure has occurred, or the lowest pressure, suction pressure, is occurring during the suction stroke. And during the delivery stroke, the lowest pressure occurs at the end of the delivery stroke. So these 2 points are very important. The suction stroke, the minimum, so the lowest pressure, that is lowest negative pressure occurs at the start of the suction, whereas during the delivery stroke, the lowest gauge value occurs at the end of the delivery stroke. So if you write these two total head values at the start of suction stroke and end of the delivery stroke, so at the start of suction, total head will be equal to Hs plus HAS, or in terms of absolute, if I write, so this is vacuum, or I can write this as equal to total head value H as equal to H atmospheric minus Hs plus HAS. So this our figure you will be getting, this will be in absolute units. Will be in absolute units, will be in vacuum units, vacuum for negative pressure. Similarly, if I write at the end of delivery stroke, delivery stroke, H value will be, so it is Hd minus HAD. So this unit will be, this will be gauge, it will be gauge pressure. Or if I write it in absolute unit, it will be H ATM minus Hd minus HAD. So this is the total pressure head value at the end of the delivery stroke, and this will be in absolute unit, absolute value. And according to, and for the separation not to occur in suction and delivery strokes, is required to, we need to have this condition achieved, HATM minus HS plus HAS, this should be greater than or equal to H separation, and this during suction stroke. Whereas during delivery stroke, it is H ATM minus HD minus HAD. So this will be greater than or equal to, this should be greater than or equal to H separation during delivery stroke. Now let us write the equation for HAS and HAD, which we have derived in our lecture class. So we have HAS equal to LS by G AT by AS omega square R. So let us find out this HAS value. HAS equal to LS, length of the suction by pitch is 5 meter, by 9.81 into AP piston area or cylinder area, it is pi by 4 into, and it is 100 centimeters, so it is into 0.1 square divided by that of this pi by 4 into suction pipe diameter 0.04 square is into omega square. Omega is not given, so omega square into R. R is L by 2. Stroke length is the stroke length value. Stroke length it is 50 centimeter. So it is 20 by 2 is 10 centimeter. R equal to 10 centimeter or 0.1 meter. So this into 0.5. So by calculating, you get this as HAS equal to, you get this as equal to 0.3185 omega square. Similarly, I can write HAD as equal to LG by G AP by suction area AD into omega square R. So this is equal to length of the suction diameter of length of the delivery pipe is 20 meter by 9.81 into this of 3 point into 0.1 square by 4 into 0.03 square is into omega square into 0.1. So this will be equal to HAD equal to 2.265. 2.265 omega square. So now let us substitute the equations for acceleration heads. Now to avoid separation, HATM minus HS plus HAS should be greater than or equal to H separation. Or so when n equal to m max, we have HATM corresponding to maximum speed. We have HS plus HAS equal to H separation. So let us substitute H separation, HATM value given as 10.3 meters minus suction head value specified as 4 meter, no sorry 3.5 meter, 3.5 meter plus HAS is 0.3185 omega square equal to H separation value is 3 meters, so this is equal to 3. So now from this equation I can solve the angular speed omega. Solving, we'll get this omega is equal to 3.454. 3.454 radian per second. Since omega equal to 2 pi n by 60, I'll get the speed value. So this gives n as equal to 60 omega by 2 pi. I can substitute 60 into 3.454 by 2 into 3.14. So I get speed of the pump as equal to n as equal to 33 rpm. So this speed value is corresponding to the condition, operation condition in the suction pipe. So when the speed is more than this, the operation will occur in the suction pipe. Now let us consider the case of delivery pipe. To avoid operation in the delivery pipe, we should have HATM minus HD minus HAD should be greater than or equal to H separation, or for n equal to n max. So when we consider the limiting case, so when this HATM minus HD minus HAD equal to H separation. So now substitute the atmosphere pressure head, which is 10.3 minus HD value. HD is suction, the delivery head value is 13 meter, 13 minus 2.265. So it is gauge pressure, so we have to put this as plus. Delivery pressure is gauge value, so it is not HATM minus HATM. So here also I have made a mistake, but also you have to correct. So this is ATM plus, here ATM plus. So this plus 13 minus 2.265 omega square is equal to 3. So now we can solve this and obtain as omega equal to velocity equal to 8.962. 8.962 per second. Corresponding to this omega equal to 8.896, we have the speed required for the pump is 60 omega by 2 pi. That is 60 into 8.962. Oh, sorry, not 8.962. It is omega square value. It is omega square is 8.962. So omega, you will get this as 2.994 per second. So this is into 2.994 by 2 into 3.14. and you will get the speed of the pump as equal to 28.6 R. So you have two values now obtained for the speed, one corresponding to the condition in the suction pipe and the second that corresponding to the condition in the delivery pipe. That means when the speed is more than 33 rpm, separation will occur in suction pipe, whereas the delivery pipe separation starts when the speed is greater than 28.6. So by considering both, the maximum speed n max will be minimum of these two values. That means 28.6 will be the minimum. So you have two set of values, n equal to 33 rpm corresponding to the separation criteria in the suction pipe, and n equal to 28.6 rpm that corresponding to in the delivery pipe. So the minimum of these two has to be taken as the maximum speed of the pump, because in delivery pipe separation will occur at speed greater than 28.6 rpm, whereas in the suction pipe it occurs only at 33 rpm. So the answer is 28.6 rpm. Third problem. Following data relate to a reciprocating pump is single acting, bore 25 centimeters, stroke 40 centimeters, speed 50 rpm, delivery pipe diameter 10 centimeter, delivery pipe length 75 centimeter. Coefficient of friction F is equal to 0.008. Compute the power saved in fitting an air vessel on the delivery side of the pump. So you have the delivery pipe dimensions mentioned, cylinder and stroke length mentioned in the question, and this data is related to a reciprocating pump which is single acting reciprocating pump. And in this case, it is asked to determine the power saved by fitting an air vessel on the delivery side of the pump. We have a delivery pipe fitted with an air vessel, so that will contribute to power saving against friction that we have to estimate. So let us write down the data. So given the bore we have given diameter which is 25 centimeter, stroke length 40 centimeter, speed 50 rpm, then delivery pipe diameter LD, sorry, not LD, for LD is 75 centimeter, length of delivery pipe is 75 centimeter, the diameter of the delivery pipe is 10 centimeter, frictional value is 0.008. So this much data are given. Then to find power saved. So this is what you have to calculate. So we have an air vessel fitted on the delivery side. By fitting the air vessel on the delivery side, we have the velocity inside the delivery pipe equal to the mean velocity of flow. So now let us solve the problem. So the friction at lows HF we can calculate by using Darcy's equation, which is 4FL V square by 2GD. In this equation, velocity of flow V in the delivery pipe has to be calculated. So now let us consider the case without friction, without air vessel. Case 1. Delivery pipe without air vessel. So when the air vessel is not fitted on the delivery side, we have velocity of flow. V D as equal to AP by A omega R. So this is the same equation what we have used in our first problem. So VD equal to AP by AD omega R. Now let us substitute the values what are known. So HFD, frictional head loss, then head loss in delivery pipe, HFD equal to 4 into 4F into LD VD square by 2G PD will be equal to 4F LT into this is AP by AD omega R square by 2 into G into P. So here omega I can calculate by the known value of speed of the pump. So omega is 2 pi n by 60. So it is 2 into 3.14 into n value 50 by 60. So this will be equal to 5.23 radian per second. So small correction we have to make. Now problem, length of the delivery pipe I have mentioned as 75 centimeter, make it 75 meter. So LD equal to 75 meter. Not it is not 75 centimeter. So that correction we have to make in the question. It is 75 meter. It is so, so this is also 25 meter. So now we substitute the whatever data we know in the equation for FD as equal to 4 F is 0.08008 into 75 is pi by 4 into diameter is 0.25 square by pi by 4 into 0.1 square into omega square, or omega is 5.23 omega 5.233 into r stroke length, not r frank radius. Sorry. So here we have L as stroke length as 50 centimeter. So crank radius will be 20 centimeter. So this into 0.2 whole square by divided by 2 into 9.81 into 0.1. So this you will get is equal to 52.34. So this is the value of frictional head loss in the delivery pipe without air vessel. Without Now let us find out the frictional head loss in the delivery pipe when air vessel is fitted. So when air vessel is fitted in the delivery pipe, velocity Vd will be equal to V average will be equal to A by S omega R by pi. So this equation we have derived in our lecture class. And this relation is for single acting pump. Now let us find out the frictional head loss when the air vessel is fitted. So HF, again HFD with air vessel will be 4 into F LD, this into AD, AP by AD into omega R by pi divided by 2 into G into DD, diameter of the delivery pipe. So now let us substitute is equal to 4 into 0.008 into length of the delivery pipe 75 into area 5 by 4 into diameter 0.25 square by 5 by 4 2.1 square to omega 2 point 2 point is 5.233. So 5.233 into 0.1 value 0.2 divided by 3.14 square. So calculating, so this divided by 2 into 9.81 into 0.1. After calculating, you will get this as equal to 5.29 meter. Now to find the head loss, power saved against the head loss by fitting the air vessel. So when we have no air vessel on the delivery side, the variation of the frictional head loss is parabolic between the end and the start of the delivery stroke. So this is HFD. So this area indicated diagram, this area represents the, so this is theta equal to 0 and theta equal to 180. We have this delivery stroke. Whereas, so this is the case without air vessel. Whereas with air vessel we have velocity constant, so the frictional head loss is a constant. So this is theta equal to 0, again theta equal to 180. So this is HFD. So this the case with air vessel. So this is air vessel and the other one is without air vessel. So now powers saved against friction by fitting the air vessel. You can calculate this as RP as equal to gamma A n by 60 into L is into. So when there is no air vessel, the area we calculate as 2 by third, as we done in the previous problem. It is 2 HFD. This is 2 by 3 of HFD without air vessel. This minus when the air vessel is fitted, the variation is not parabolic, so the friction is head loss is constant, so it is this minus HFD. FD with air vessel. The head loss, the power saved is equal to the power saved delta P equal to gamma 9810 into area pi by 4 into 0.25 square. Period is 50. Top length 0.4 divided by T is into 2 by 3 of 2/3 of without air vessel, the frictional head is 52 point, so this into 52.34 is minus without air vessel, sorry, with air vessel it is 5.29. So 5.2. So 2 by 3 of 2 by 3 into 52.34 is value minus 5.29. By calculating, we can thus power saved delta P as equal to 1.696 kilowatt. So this is the power saved against friction when we fit an air vessel on the delivery side of the given single acting reciprocating pump. So that completes our problem 3. Also, that is the end of the tutorial. Okay, thank you very much.